in temporal difference learning, we're trying to solve the prediction problem, predicting the value function, but and we're sampling from the environment like we are with Monte Carlo learning, but we're also taking advantage of this bootstrap relationship that we have, which is what we're going to use the value at the transition state as well as the reward from the transition to estimate the value. And this just follows from the definition of the value function, which also follows from the definition of G, which isn't listed here, but that's, the value at state S is supposed to be the expected value of all of the future rewards we obtain from state S under whatever policy that we're following at the time. So because it's the sum of all the future rewards, and each value is that, we can take this bootstrap relationship and have this sort of recursive definition of the value function using the values at transition states. And to sort of highlight the differences between this and Monte Carlo prediction, where so in Monte Carlo prediction, we just directly sample G because we just create a trajectory through the environment. And once we have the full trajectory, we then can explicitly calculate a value, which is G, by adding up all the future rewards. And that calculated value is an unbiased estimate for the true value under the policy. So that's the Monte Carlo method. Now we're talking about this TD0 or one-step TD method, which instead we're going to sample a single reward, and then we're going to use the estimate we already have for the transition state. And there was this random walk example, which is simplified because in this example, we have no actions. There are just steps that are taken. So we always start in this middle state C, and then with equal probability, we transition either left or right. And if we are in state E and we transition right, we exit to this terminal state with a reward of 1. And if we're in state A and we exit left, we end up in this terminal state with a reward of 0. So depending on where you randomly exit this chain, you'll get a reward of 1 or 0. And then now we don't have to worry about a policy because there's no policy, there's no actions to take. It's just, it's all random. And we want to calculate value estimates for each state. So that's like, what is the expected, reward from starting in state C? So the expected reward in state C, it should, it relates to the probability of exiting to the right or to the left after we bounce around in this environment. So there's an exercise where you calculate these values, but here I also have this little. Okay, so this is the environment that we're talking about. So we have this chain, and then hopefully this works if I run this. But we sort of bounce around, and eventually we end up, either right or left. So here, this is like a 5-step, episode, and it ends right. And if I make a new one, if I recompute this, in this case, it's a 7-step episode, and it exits to the left. So, because of the symmetry of the problem, that there is actually an equal probability of exiting right or left, but which means that if we start in state C, it should be kind of obvious that the value of this state is 0.5 because we either have a reward of 1 or 0 with equal probability. What's not as obvious is the value of all the other states, although it turns out that those values in this 5 state chain are just all the fractions of 1/6. And here, what is happening is we're sampling trajectories through this chain. And this is comparing using TD learning or Monte Carlo learning to calculate the value. And this is, the error with respect to the true value. So these plots are showing after, 10 episodes of samples, this is what the expected values that we have compared to the true values. And the true values is this straight line. So the point here is that for this particular environment, it seems like the TD learning consistently has lower error estimates than Monte Carlo learning. And that, over a range of step size parameters, alpha. This is the free parameter that controls how much we change the value estimates at every update.
It seems to be obvious. I mean, I don't know if I understand the problem correctly, right? But with Monte Carlo, you do not update your knowledge that you just did, whereas the other one, actually, no, there is no policy here. So how would you? Maybe you are going to talk about this, but Monte Carlo understand is completely random. TD is what again? Is where you incorporate the knowledge of the previous step into your model.
Okay, so the update rule, actually, I wonder if it says it in the book. So for both methods, and actually this is earlier in the chapter, but there is a direct analogy between the two. So both methods will converge to the correct value. That they both correctly estimate the value. It's just a question of how quickly they converge in different situations. In the case of TD learning, so for both methods, we're going to go through an episode and we're going to have all these samples from the episode. In TD learning, at every step of the episode, we do this update where we make use of the value at the transition state. In the case of Monte Carlo learning, we do this update where the value G that we're using is a sample of G. So we actually still do an update at every state along the trajectory with Monte Carlo as well. So they both, imagine for both methods, we have the same episode that we are dealing with. It's just a question of how we're using the data. But for Monte Carlo,
so how do you interpret the result that Monte Carlo takes longer to converge? I'm not so sure that I don't see the graph anymore.
Well, here's the graph here. So so there is an exercise that deals with this. In fact, to build intuition on this, maybe we should just talk about this. I think what we already finished these exercises, but let's just review quickly on maybe 6.5. Actually, no, 6.5 is a little tricky, but I do have an explanation for that too. But let's look at 6.6. So the question in 6.6 is, we have this random chain. Describe at least two ways that you can compute the true values for this chain, the true values. So here's one of the methods that you can do. You can set up a system of equations and you can use the relationship between all the values, right? So we have the value at state A is equal to the value at the state to the left, which is 0 by definition, and the value to the state to the right. And there's all this 0.5 probability for each. So this is a system of 5 equations, 5 unknowns, and you can solve it. And when you solve it, you end up with these fractions. So that's just being shown here. Now imagine you think of another method that would solve this. So here's another method. We're trying to estimate the value at state A. So and we're trying to add up the values. We know if we exit left, the values are 0, so we don't have to add them. We only have to add up the rewards of 1 weighted by the probability. So we basically need to compute at state A the total probability of exiting to the right, right? That's what's going to be computed here. So you could get out to the right by going 1, 2, 3, 4, 5. So you take 5 steps, and that would have a probability of 0.5 to the 5th. Then you could also add a turnaround. So you could go like 1, 2, 3, 4, 5, 6, 7, right? So that would be a 7-step episode. But there's like 4 ways you could do that turnaround depending on where it happens. and so forth. There's actually an infinite number of these things. You have to weight them all and add them up. And this would be kind of complicated to compute. In fact, I don't even know if you could, how well you could compute it. I mean, you could actually compute it with like Monte Carlo, but so anyway, this method is analogous to the Monte Carlo method where we're sort of estimating state A by looking at all of the ways that we, out to the final exit point. Whereas in this method, we're using the relationship between them. And, so this method's clearly harder to do. So essentially, like the Monte Carlo method is not making as efficient use of the available data because it's not using the relationship between the states at all. So it still works fine. But in this particular example, all of the information is at the end. And the relationship between the states is very helpful in values. So that's one piece of intuition why the TD method works better. But it depends on the environment. In this environment, it works better. There's other environments where maybe it would not work better. That was sort of also covered. If you read the earlier part of the notes, there's this whole driving home example, and I kind of elaborated on a situation where the Monte Carlo updates would actually be better. But there's also a case where the TD updates are better. But you can read in the, we can look at it later. But there are various arguments. But this isn't like a hard rule. TD isn't always better. It just happens to be better in this situation. There is this other exercise which is a little subtle, but it's the question is why for these TD methods, why does it seem like it hits this minimum before converging to a different value in the TD method? And there's sort of a hint that maybe it has to do. So remember that we initialized this at 0.5, right? All the values. And that's the middle value is 0.5. So to get some intuition about this, so here I solved the problem again, but now I initialize the values at 0 instead of 0.5. You can see here, there's no minimum that occurs. And the reason why the minimum occurs is because if you look at the TD updates, you first update the end value, either this or this, depending on where you exit. And then the updates sort of propagate through, and they're centered at 0.5. This black line is the true values. So the way these updates work is the line kind of tilts up towards the true values. And even if the alpha is large and we overshoot, like see this blue line, this is after 99 episodes. And here the values have overshot because the step size is too big. So we've overshot the true values, and it's gonna end up converging to a value that's slightly off because of the step size. But along the way, we end up passing through the correct values just because of where we happen to have started. So like the line kind of overshoots, but it passes through the correct values. Whereas if you initialize it like this, you could see it never passes through the correct value. It's just all the values are getting closer, and eventually they'll converge here. But because of the way this was initialized symmetrically at the correct value for C, we end up with this sort of lucky pass through the minimum. So I don't know. This is for 6.5. It's sort of it doesn't matter too much as an exercise. It's just sort of, worth knowing that sometimes you pick a lucky initial value and it helps out with the answer. But does that make sense to everyone? I don't know if anyone was confused by this question.
So if I understand correctly, obviously it says that the RMS error is, so you're trying to estimate the value of which are all set at 0.5 initially. Then, but this is again, what is this value? The TD values. It's an expected value of.
These are this is all for TD estimation.
Okay.
Yeah. It's just that like these lines all represent what the estimates are after every, a set number of episodes. And you just see that the way the updates function, they sort of, the values end up symmetrically moving to match this line, and they end up just sort of passing through it.
I'm just trying to understand, like, what does that mean that the error is smaller, which, the other graph, empirical RMS?
Well, here I just initialize. I
I'm talking about
the
one, yes. You initialize them to 0, they increase, all of them.
Mm-hmm. Yeah, eventually they'll converge to this line as well. But it's just
I'm talking about the first section where you have like close to the first row of graphs, not this one above. You were there. You were just going too far. No. They were 2 graphs. I mean 4 graphs, but the top 2. Yeah, the top 2 here.
The top right one.
Yes, the top right one, exactly.
Yeah.
So I see at 20 episodes, or that's what I read. 20 episodes, the error is the smallest it will ever be, right? So why incidentally it increased. So I'm just if the error is smaller, it means that where is the solution degrading over time after more episodes? I don't quite understand that.
It's not that it's degrading, it's just that here the step size is too low. Like, so for this to converge properly, the step size needs to also go to 0 over time. If you have a finite step size, this is just noise. Like these updates are going to create noise around the true thing. So this is what it's converging to. Just like here, it's actually the same thing, right? The error is like 0.08 or something.
Okay. So you think it's due to the learning rate or step size, or?
Well, the reason why it's not converging to 0 is because the step size is too large.
Okay.
But the reason why it passes through this minimum here is just luck. It's just because we have a lucky initialization. Okay. So basically, along the way to overshooting, it passes through a minimum error. But it's just luck, because like if you initialize it here, you don't see that, right? Or like up here. It's just because we started at 0.5, which is already the correct value for C. And all these are symmetrical around 0.5. Okay, so that, so initialization, a lot of these effects, weird effects you see could be due to initialization is the main point. Okay, so there's another discussion here in the book about what TD0 is converging to compared to Monte Carlo learning. And they introduced this idea of batch updating. Now, in batch updating, what happens is, let's say you have like one episode here. So you have the data from one episode. And normally when we apply this learning, we will do a single set of updates through the states for that one episode. And then before we do a new set of updates, we're going to get a new episode. So like we're just doing the state updates, matching each episode. In this batch updating, what we're going to do is have a set amount of data from however many episodes we've collected so far. And we're going to do the state update with that data, and we're going to repeat it until it converges. Because in general, like these values are not yet converged. So we're going to converge the value function completely, given just the available data that we have. And this method will also converge just like the other method. It's just that we're wasting a lot of time in each episode, basically, because we're like insisting on this value function converging before we even have enough, data. Like normally you just keep adding new episodes, right? And every update is like a fresh transition. So here, also, the TD method on the limited amount of data has a consistently lower error than Monte Carlo, which means that somehow with incomplete data, the TD learning seems to have an advantage for this particular problem. And this is another question that's brought up is, why is TD learning better when the data is limited? So something to think about. There is, and so here's another yeah, this is an example of the batch training. And what, yeah, and here I have it set up where you can change the learning rate. You can see under a wide variety of parameters, the TD method is better out. Now, if you allow the episodes to grow to a very large value, and the learning rate is low enough, then both methods should eventually converge. But again, like the Monte Carlo also seems to be more sensitive to the learning rate, which was true in the other graph too. So yeah, there is this sort of consistent advantage for TD. And the question is why? And one of the justifications, so if you think about this example here, we have this example of this very simple contrived MDP, where we have a state A that we start in, and whatever happens in state A, we always go to state B, and there's no reward. And then from state B, we have a 3/4 chance of getting a reward of 1 and a 1/4 chance of getting a reward of 0. And then there's 8 episodes here. Oh, sorry. So actually, we don't always start in A. So in this case, there's an episode where we start in A, we go to B, and then we exit with a reward of 0. And then there's a bunch of other episodes that are starting from B. Okay. And from B, we sort of observe, a number of 1s and then a 0. So this isn't the 1, 2, 3. So there's 7, and it's a noisy process. So even our estimate of B is not going to be exactly correct. Oh, wait, actually, so we have 8. So from B, we have 8 examples of transitions from B, and 2 of them are 0, and 6 of them are 1. Yeah. So this is set up so that actually our estimate of B will be correct, right? Because the correct value of B is 3/4. So the question is here, if you use this data, and you can either use Monte Carlo, right, or you could use TD learning, and you end up with different estimates. So actually, for both methods, the value estimate of B will be the same. So we'll have a value estimate of B, which is 3/4, right? For both methods. But for Monte Carlo learning, our estimate of A will actually be a 0, right? Because we only have 1 episode starting from A, and what happened was we transitioned to B, and then we exited with 0, right? But if we use TD learning instead, what we're going to do is we're going to estimate our value of A by taking the reward of 0, but then adding to that our estimate of value B, which in this case will be 3/4. And the value of A then will be 3/4. And that's actually the right answer, right? Both A and B have the same value of 3/4. So obviously, like for this example, with this data, we actually know what the MDP is, right? And this data, like if you only had this data, right, you wouldn't know what this MDP is. But with TD learning, what you're doing is you're sort of taking the data and you're trying to reconstruct this MDP from the data. Whereas with Monte Carlo learning, we don't really consider the MDP at all because each state value is just an estimate of the trajectory from that state. Like all we need to know is the future rewards we get. We don't have to know anything about, the other states.
Mm-hmm.
So there's a term for this, which is the certainty equivalence estimate, because it's the estimate, it's saying if this data, if we had a certain estimate of the MDP from this data instead of an approximate estimate, then the value estimates are going to match that MDP. So it's almost like with TD learning, we sort of build a model of the MDP from the data, and then we evaluate that model, like the values to convergence. Whereas for Monte Carlo, we are just calculating, the maximum likelihood estimate of each state from the available data. Now, of course, if we have infinite data, both methods will converge to the same thing. But in the case of limited data, we can see that the Monte Carlo estimate in this case, it doesn't make as efficient use of the data because it's not taking advantage of any of the relationships between the states, right? Because it's saying, well, we only have one trajectory from state A. That's true. But we know that state A transitioned to state B, and we have a lot of information about state B. And in Monte Carlo learning, we don't use any of that information. Whereas in TD learning, we're going to use all the information we know about B to help us with the estimate of A as well. So that's yet sort of another piece of intuition as to why TD could be better. So does that, any questions about this?
No, I think you explained it well.
Okay. Exercise 6.7, I don't think we really have to go over it. It sort of relates to this importance sampling, which we haven't even talked about yet. But if you want to read about it, I have an explanation here. And luckily, in this chapter, I don't even think there's any off-policy learning that uses importance sampling. So yeah, I think we can skip this for now. If you want to read about it, it's in the notes here. So let's move on to Sarsa, which is now the control. So everything we've dealt with so far is the prediction problem, right? So we have a policy, and we're trying to predict the state values under the policy. And in the control problem, the goal is to compute the optimal policy. So we already had the Monte Carlo control in the previous chapter. And now we're going to talk about Sarsa, which is TD control. And the reason why it's called Sarsa is because we have a trajectory. And the trajectory, we have state, action, reward, and then state, the next state action. I mean, it's just they just sort of cut off the acronym there. But, you have this chain of all these values, a chain of these trajectories. And just like we did with for Monte Carlo control, we are going to use the state action value instead of the state value. And this was sort of an important point earlier, but if you use the Q function for the state action values, you don't actually need to know the full environment dynamics to solve the control problem. And that was sort of explained in chapter 5. But if we, right here, we're talking about environments where we don't have the full transition function. Like all we can do is collect data from the environment. We can sample from it. So in that restricted regime, we have to build these Q estimates. And then from the policy improvement theorem, if we have the Q estimates, it's very straightforward to compute the optimal policy, or to do policy improvement, because all we have to do is look at a given state, look at all the Q estimates for all the actions, and just select the action that maximizes the Q value. And since we already have all the Q values, we can just look at them and find the maximum. We don't have to compute anything to do that. So this represents the Q update we're going to do for Sarsa. So this Q update ends up making these state action value estimates represent the policy that is being followed, or like the policy that is creating this trajectory. And then we do a step of policy improvement where we update the policy. We make it greedy or epsilon greedy, as we'll see, with respect to the Q function. And then that just continues indefinitely until the Q values converge. So it's the same as Monte Carlo. It's just that now we have a new update rule. Right. And this update rule represents the Bellman, optimality equation that we had before, right? Because this is establishing, what are the Q values with respect to the future, the transition Q values. Okay, so let's see. What is exercise 6.8? Show that the action value. This, I don't think we have to go over it. Again, this is like a pretty mathy problem, but it's just showing the relationship between the TD error and the Monte Carlo error, because this term is the Monte Carlo error, where we're using G, where G is like the full sample for the future reward. And just like for the prediction problem, the point is just that they have a relationship to each other, which you can derive here. You don't actually use this relationship in any kind of algorithm. It's just showing that there is, you can establish some kind of equivalence between the two methods. Or you can at least express the updates from one method in terms of the updates from the other method. And there's a number of these weighting terms, but for a given episode, the updates are going to be different. So here is the pseudocode for Sarsa. So there's pseudocode here, and then there's sort of one version of implementation here that I have, which is very similar to the implementation for the Monte Carlo control. But just like Monte Carlo control, we create, a series of episodes. We, go through the episodes. We get a trajectory. And then for each step of the trajectory, we're going to perform this update. The difference with Monte Carlo was that, one of the differences was that we couldn't actually do any updates until the episode was complete, because we wouldn't know what the G value is until the episode's done. In the case of Sarsa, we can do an update as soon as we have the transition state, right? As soon as we know S prime, and in this case, we actually have to get A prime as well. A prime will come from the policy, and then we can do this full update. Here we can use A prime because we're going to end up taking the A prime that we get from the policy, where the policy is the epsilon greedy policy derived from Q. Right. So that just means that we most of the time pick the action which appears to be maximizing from Q. And then with a probability epsilon, we take a random action. And just like with the Monte Carlo from before, the reason we have to do this is because this method only converges if we're guaranteed to visit all the state action pairs an infinite number of times. Right. So this ensures that we visit an infinite number of times. In other words, it ensures proper exploration of the environment. Yeah, and so you can see here I have we've implemented this. Yeah, when you create the greedy policy from Q, the way I've done it here is there's different ways of doing it, but in one version, if you want to make an epsilon greedy policy, you basically find the maximum value, and then you create a policy that, where the action choice matches whatever the maximizing action is. The reason why there's all these other steps in here is because if you have like multiple maximizing actions, you're supposed to randomly pick between them. So you have to handle those cases as well. And for the greedy policy, you don't have to reserve this probability epsilon for any other actions. So are any questions about how Sarsa works or how it's implemented?
So it seems like the only difference between Sarsa and the previous Monte Carlo is that the previous Monte Carlo accumulated the rewards from the goal state and then updated one step, while here it's basically updating at every single Q value at each step.
Yeah, it's updating. Although in the case of here, if I find the, well, I'm just trying to find the Monte Carlo. Well, I can run this, but in Monte Carlo, we also will update the Q value for each step. It's just that we have to wait until the end for those values to be updated. Let's see.
You mean to the end of the episode, right?
Yeah. Yeah, but every state visited will still receive this update. It's just that the update is going to be based on this G minus the current value of Q, where G is what we know is the future reward. Mm-hmm. And here we only need to know the transition state to do the update. So yeah, the things, in this case, the policy can change during an episode with Sarsa because, right, we choose action derived from Q, right? But we're changing Q at each step. Whereas in Monte Carlo, we will, whatever the current policy is, we will compute that, or we will compute a trajectory from that. And then after we have the episode, we'll do all the updates. I mean, you could also do Sarsa without updating the policy during an episode. It's just that typically you do, because like, why not use the information immediately? But you don't have to do that. Like you could do these updates and you could wait to update the policy until after the episode was finished. That would be fine too, because yeah, either way, it will still converge to the same thing. Yeah, so for Monte Carlo, we there's a step here where I get the entire episode, and then you typically step through the episode backwards with Monte Carlo, because that's the easiest way to compute G without wasting any computation, right? Because you accumulate it from the end going back to the start, because that's the easiest way to compute G, because it's the sum of all the future rewards. So you can always start at the end where there's no future rewards, and then you just keep adding them as you go backwards. Okay, so yeah, also in Sarsa, you can have some initialization. Like there's different ways of doing it. In this case, you initialize the episode at some normal starting point for the environment. And then the epsilon is what guarantees that you sort of explore everything until you reach a terminal state. This is designed where this is for episodic tasks still, where we have a terminal state. But this method can also work for tasks that aren't episodic. It's just you have to change the setup a little bit, where you have to, instead of going through episodes, you have to just go through steps, and then you have to have some point at which you stop doing more steps. Okay, well, so if there's no questions about Sarsa, we can look at the first example that makes use of Sarsa, which is this windy grid world example. So this is a grid world with these actions. These are just like rectilinear actions. You can make a single step in each of the 4 directions. And this is the starting square, and this is the goal, the end square. And the problem is set up so that there is a reward of wait, how is this set up? I think there's a reward of -1 for each step, right? At least that's what I think it is. forget how this works. Yeah. Okay, yeah. So you have a reward of -1 for each step, which is a really good way to set this problem up because you don't have to use discounting at all, and it makes it so the agent is trying to reach the goal as quickly as possible. Because any added step is going to add a reward, an additional negative reward to the problem. Now, without the wind, you would just sort of walk straight across and get to G. But there are these wind values that end up pushing you up a set amount every step. So if the wind value is 1, it just means that if you try to step to the right, you'll end up also stepping up 1. And with 2, it's like you end up stepping up 2. So here, I'm showing an example of this is if you just follow a random policy. This is like a trajectory through the environment. Also, if you try to step out like an edge, you just stay in the same place. So you don't go off the map or anything. And you also get a reward of -1 for that transition. So they're showing here the optimal trajectory for this environment with these actions. So this is the path you end up taking. And this was solved using Sarsa with these parameters. So there's an epsilon of 0.1, which means there's a 10% chance of taking random actions. And the step size is 0.5, which is, in here, the step size just controls this update. And all the Q values were initialized to 0. And this line is showing, so when this becomes a straight line, that just means that the policy has converged so that every episode is taking an equal number of steps. So here, let me show a little more examples of this. So, okay, so this is here. If I run this again, see in this case, because Sarsa, it depends on sampling from the environment. You don't always get the same answers. Like it might not actually converge to the same values. You can see here. Sometimes when I run this, the path it finds isn't actually like the best optimal path. But what I'm showing here is a solution which is correct because this is the value iteration solution, which is from chapter 4. And the nice thing about value iteration is if you actually know the full dynamics of the environment, like this is guaranteed to just be the correct answer. Like that, there's no random sampling involved in this. So you see this matches what's in the book. This is the optimal path. You see sometimes when you run Sarsa, like it's finding this path, which isn't exactly optimal. I've also added, in addition to this plot, this is showing the steps per episode as Sarsa is running. So you can see it is converging down to this value. If I ran it longer, you would see more. I'm not here showing the training fully. So here, this is closer to the optimal path. So this is showing on the left is the policy. And on the right is the value function. So when you finish with Sarsa, you have the value estimates. Or in our case, we actually have the Q estimates, right, which we can turn into value estimates using the policy. So if this value is -16, it means that if the agent is starting here, it thinks it'll take 16 steps to reach the goal. Now, the actual optimal policy is 15. And if I reran Sarsa, it would probably, it could match this value. It just depends on the parameter. See, now it's saying 17, 18. But it's both a combination of picking the right parameters and also running it for a long enough number of episodes. But you can see, it's close to the optimal answer. Now, the reason why I included the value iteration solution here, just because sometimes it's hard to tell exactly what is the optimal policy in all the cases. But with value iteration, you can always just see exactly what the optimal policy is, including all the equivalent actions. So in this case, this is the value iteration solution, which is just, it basically goes right everywhere. And then when you get to the very edge, that's when you try to do this turnaround to get back to the goal. right? So there's no reliable way to get to the goal without making this path. And you can see for Sarsa, it's sort of like finding the policy, but it's not nearly as precise as this. Like it's clearly making mistakes. Also, these states here for Sarsa, these appear to be states that weren't visited when we ran Sarsa. So it doesn't really have an update for this. Now, in this problem, it doesn't really matter because, right, if we follow the optimal trajectory, we're never going to end up here. So we don't actually need good estimates for these states. But strictly speaking, to have correct value estimates, we do need to have like proper estimates for every state in the environment. I guess I didn't really show the code that creates this grid world, but for creating the grid world, like the way I've set this up is you have to define the state space, which in this case, the state space are all of the squares. The actions in this case are just these 4 actions, up, down, left, right. And then you have to have a way to initialize the episode. So in this case, whenever you initialize it, you always start at the same square, which is here. And then there's a transition function, which just does a step. So the way the transition works is you give it a state action pair, and then the output is a reward and the state that you end up in. Right? So this step function lets you create a trajectory. And then I also added, there's this function to check if a state is terminal, which just allows you to end the episode. Okay, so this is all that's required in terms of defining the MDP for doing this. And then you can apply Sarsa. In order to apply value iteration, you actually need to define the full transition function for this, which is not really talked about or mentioned in the book, but I did. It is possible to do it. It's not too bad in this case. But here, in terms of creating the probability transition function, you just have to know for every action from every square what the probabilities are of ending up in every other square, which in this case, it's basically like a deterministic problem. So the probabilities are very easy to calculate. But it is like more cumbersome. Writing this, defining this is a lot more cumbersome than just the transition function. But, in this problem, it happens to be pretty trivial to do. So, yeah, any questions about the Sarsa solution to the grid world?
Well, the solution makes sense, given that that the optimal policy would be, basically going all the way to the end because of the wind factor, and then given, the code example of defining all the states. States makes sense.
Yeah, and like this is designed so that if you step to the bottom of the grid and try to go across, the wind will push you past the goal. So that's why you have to go around here. Okay, so now there's a series of variations on this grid world example, and one of the variations that's introduced is additional actions. So here I've added 4 new actions, and those are the diagonal actions. And this helps a lot because you can see a diagonal action is actually 2 of the previous actions, right? So we're basically moving, we're like sort of taking 2 steps for 1 with these diagonal actions. So then the exercise is, solved. So the way I've written this, I can add actions. It's pretty easy to just, solve the problem this way. So this is the solution when we add diagonal actions. And you can see now, well, the path, in this case, Sarsa, this is the true optimal path. The Sarsa path is, again, very similar. And now we can see that as this is converging pretty quickly, we end up with a number of episodes that are finishing in 7 steps when Sarsa is running. These spikes also, part of it is the epsilon, right? Because I'm using an epsilon of 0.1. So these trajectories are never going to be perfect because, whereas here, when I'm plotting the Sarsa path, I'm getting rid of the epsilon. So I'm just taking the greedy policy at the end. But while Sarsa's running, it's following the epsilon greedy policy. So again, if you look at the value, so the value iteration solution here, you see it's very precise, much more precise than Sarsa, because, like, for example, these look like this because from this state, all 3 of these actions are equally optimal. Whereas, in Sarsa, you're not going to get that level of precision with, although here it did correctly learn, right? The starting value is -7. So here we can get to the goal in just 7 steps instead of 15 up here, because you could see what it's doing is that as it starts going across, it's just taking these down diagonal steps here every time to get to the goal. And then the wind is pushing it up. So it's sort of going down low enough and then taking the down right diagonal steps to get to the goal.
Yeah,
so
because new moveset, it makes sense that it has the right down move basically is sufficient to overpower the wind coefficient if it goes low enough.
Yeah, there's another important difference here also, which is that the starting state here has the lowest value, or at least it's tied with all these other values. Whereas now with this new solution, actually, like this state has the lowest value. Like if you were to start here, it would take 9 steps to reach the goal, whereas this starting state only takes 7. And if I modify this, you could see what the optimal trajectory is starting from this state as well. But it looks like based on the policy, you would end up having to sort of go to the right and then down around again if you end up here. And that's faster than actually trying to go down to here and then across. So, yep, this is the solution with, it's called like the king actions, where you can basically move in any of these directions. So any question about this new optimal policy? Okay. So then there is an additional variation. It's pretty similar, but this one just adds a new action to the king actions, which is an action where nothing happens, where you can just choose to not move at all. And the trajectory is actually it is different, right? Yeah, it gets rid of this kink here. I don't actually know if that's a real. Yeah, so it doesn't actually, I don't think, I think this might just be also adding the kink or not is just part of the random variation in the policy. You could see that the optimal policy has equivalently good actions. Like each of these 3 are equivalently good. But this doesn't actually change the value estimate, right? It's still 7 steps. However, there is one minor difference. The one minor difference is in this state. So this state is 2 steps under the goal, and it has a value of -1. And if you look back at here, this same state here has a value of -2. Now, we don't actually try to ever end up in this state following the optimal policy. But I guess the point is, if we add this stay action, we can actually just not move from this state. And then we'll end up in the goal because we'll get pushed up 2 squares. Whereas if we're forced to move, then it's worse because you have to actually move somewhere. So that's the only difference I could find between these 2 policies. Otherwise, everything's exactly the same. And starting from the starting state, you don't actually, do anything differently. So that is basically the end of the windy grid world example. At least for, all the variations, adding steps. Is this any question about this? Okay. The only remaining variation is to add stochastic wind. Now, in this example, then, and this is one of the exercises. So in the stochastic wind example, there are three different possibilities that can happen when you encounter a square with wind. So basically, if you're in a square where there's no wind, then it's the same. If you're in a square with a non-zero wind value, then you have a 1/3 chance of experiencing that wind. You have a 1/3 chance of the wind being one larger, and a 1/3 chance of the wind being one smaller. So now it's no longer a deterministic environment. Question is, can you solve this with stochastic wind? I also can implement the stochastic wind with value iteration as well, because you know the exact probabilities of everything. So Sarsa was also able to succeed in this, mostly optimally. But you could see the training process is definitely a lot messier with stochastic wind. Well, let's just see what it ends up converging to. So Sarsa does succeed in this problem, but at least the way I've set it up, it's definitely needs to run longer and with probably different parameters to converge to the true optimal policy. Because here, you could see it's estimating it will take 20 steps to reach the goal. Whereas actually the true answer is 11 steps, which you can get from value iteration. And this as opposed to the 7 steps from before. So making the wind stochastic does make it harder to reach the goal. But the optimal policy is substantially different, right? So this is the value iteration solution. And I guess because of the stochastic wind, the most reliable solution is just to go down as low as possible and then try to reach the goal going across. And that's what you can see the policy is here, where it's making these diagonal down steps as opposed to the previous optimal policy, which is okay with going straight across from the start. So you can see it's a lot harder to see what the optimal policy actually is with like Sarsa or with Q-learning or any of these other techniques, just because you don't have as precise of an answer. But here you can clearly see that it creates this preference to going more down to the lower part of the grid to reach the goal. So yeah, if you're solving this yourself or trying to apply Sarsa or something else, you should say the correct value estimate for the start should be a -11, at least based on what I did. And actually here, you can also see in the solution, there are now like decimal values, which is because the wind is now stochastic. So, now that there's no longer like a certain number of steps from these squares because, there's a probability of the wind value being different than this. Yeah, so I think that's actually like the end of the grid world, the windy grid world. There are no other variations. Good. Any question about this?
No, I did not have any questions for the windy grid world examples.
Okay. So that concludes the section on Sarsa. So the next section is on Q-learning. which is definitely more, I think, more famous than Sarsa at this point. But Q-learning is very similar to Sarsa. And actually, I'll go back where Sarsa is defined. So this is the update step for Sarsa, where we are using the Q value at the transition state. The difference in Q-learning is instead of taking the Q value at the actual transition state, we take the maximum value at the transition state. So regardless of what the action actually taken is, to do the update, we're going to use the maximizing value here. So if you compare these two, see the difference? It's a pretty, that's the only difference between the two. Now remember, for Sarsa, the action is selected by the policy, which is derived, in this case, by the epsilon greedy policy with respect to it. So it will oftentimes be the maximizing action, but in Q-learning, we are always going to take this max here. So, and then of course there's pseudocode that implements it. It's not that's the only difference. Everything else is the same. We're still going to follow the epsilon greedy policy, which ensures that we visit all the states. So this is Q-learning. I did also run it on the grid world, so you could see Q-learning does quite a good job solving the grid world. In fact, this -15 is the correct value. -7, -11. So actually, yeah, Q-learning, well, this doesn't explain why Q-learning is better than Sarsa, but in this case, you can see that these solutions are definitely had an easier time getting the optimal solution with Q-learning than with Sarsa. And at least these values from the starting state are actually correct in every case. But to sort of illustrate one of the interesting properties of Q-learning, there is this cliff walking example. Now, in this example, it's just a grid world, just like before. There's a start, there's a goal, and there's a cliff. And if you step into the cliff, you get a reward of -100, and you're returned to the starting state. Otherwise, you just get a reward of -1, and you're trying to reach the goal. So it's a very simple environment. The optimal path, obviously, is just to take the shortest path here, which hugs the cliff. Now, the point they're making here is that when you do Sarsa or Q-learning, so Q-learning, we'll see, is going to end up learning like the policy that Q-learning follows. Actually, let me just see here where the so the policy that Q-learning follows is going to be closer to the cliff than the path that Sarsa learns. And, you know, because of that, while it's training, because it's following the epsilon greedy policy, where there's a 10% chance of taking a random action, there are going to be times when the agent actually goes off the cliff during Q-learning. And because Sarsa ends up learning the safer path, it eliminates most of the cases where we just get unlucky and we randomly fall off the cliff. Now, it depends on what we're actually trying to learn, but because like if we were in a case where there's no randomness to our actions, like we can always take an action and not be forced to take a random action, then we do want to make this path. But if some of the time we are going to take a random action, then we would want to take the safer path, right? Because we're not gonna, so it depends on, in each case, we're sort of asking the algorithm to learn a different thing. And because of the way Sarsa is designed, Sarsa is learning the optimal policy, but under the constraint of whatever the epsilon value is, which is why it learns the safer path. Whereas, Q learning is, because of the maximization step, this is actually going to converge to the optimal Q value policy without regard to epsilon. Like epsilon doesn't come into play here. So then if you derive a policy from this, it's just going to end up deriving a policy which is closer to the optimal policy, which is also going to follow during training, which is why it ends up falling down the cliff. So, this is showing like the Q learning path falling off more. This is showing like this is actually the optimal path learned by Q learning, which is the path that hugs the cliff. Whereas in Sarsa, it's learning the safer path. And then this is also average. Yeah, actually, what was your question?
Oh, not a question. So basically, that's basically a limitation of Sarsa based on the randomness. Well, the epsilon greedy randomness, essentially.
Yeah, I mean, in this case, though, it's like, so if when you actually are in this environment, you do have this randomness, like with epsilon, like to take a random action, then you would actually want to take the Sarsa solution, because that, if you hug the cliff, there's a high enough percentage of time you hit it that even though like the path is shorter on average, or like if you take a typical path where you don't fall off the cliff, this path is shorter, but the negative 100 ends up canceling out the benefit of that with that particular epsilon. But this example ties into this exercise question, which is why is Q learning considered an off policy method? And it's an important question because we don't actually have a behavior. I mean, like in previous examples, we had like a target policy and a behavior policy. In this case, we only have the behavior policy here, which is actually creating the trajectory. But we do have this update step with the max. And this is why it's, considered off policy. But is someone else can answer this, or I can just give the answer, but does anyone have an idea or a good explanation of why Q learning is actually off policy, whereas Sarsa is an on policy method? Well, I mean, it really comes down to the fact that the behavior policy is epsilon greedy. But if you look at this update step, this is the update step, which is analogous to the Bellman optimality equation for the Q function, right? So this update should end up converging to the optimal Q function. Whereas the policy we're following is actually the optimal epsilon greedy policy for the Q function rather than the optimum. So this ends up being off policy because the Q function we're actually computing is the optimal one, but the behavior policy we're following is based on the epsilon greedy rather than the greedy policy. And you can see that clearly by, for this to be on policy, this value here would have to always match the Q value at the the action we take from S prime, right? But because of the epsilon, there is some probability that the action we take at S prime won't actually match this maximum action. So the times it doesn't match, this is essentially like an off-policy update. So any questions about that?
So from all the actions that are available for the Q state t plus 1, because the max entry might not necessarily be what the best action would be from the Q epsilon greedy.
Well, I mean, it's more that the policy followed by the epsilon greedy is not necessarily the best action, because there's this probability epsilon it takes a random action.
Yeah.
Whereas, yeah. And then let's see, what is this exercise? Suppose action selection is greedy. Then is Q-learning the same as Sarsa? Will they make exactly the same action selection way? This is a bit of a subtle question, but it's saying that, let's say that when we take actions, we get rid of this. Now, forget the fact that this won't work because we've now removed the exploration. So this is no longer guaranteed to converge. But let's just forget about that and say we actually take actions derived from Q where Q is now greedy. Right? Now this is sort of no longer off policy because this max will actually match. Like now the action should always match the maximizing action. However, there is a slight, there are cases where it doesn't happen. So let's say we do this update, right? So we're updating Q. Now, in terms of selecting action A at the next step, that happens up here after we've done the transition to S prime. So if the Q function hasn't changed, like from here to here, then when we go to pick an action from S prime, we're just going to pick the action that's maximizing. And this will match, and it will be exactly the same. But there is one case where this might not match. And that's the case where S prime is equal to S. Right? So if the state we end up in is the same, then we actually will update the state value estimate for the transition state on this step, right? Because S is equal to S prime. And depending on what the update is, it's possible that when we evaluate the action on the next step, that we might pick a different thing, right? Because this was calculated from the old values of Q. So the only subtle exception with this differing from Sarsa is if we repeat a state. So we end up in the same state consecutively in an episode, then it would be possible. So that's just, yeah, I don't think that this isn't too important of a distinction, but it's just, that there is a slight difference here of taking the maximum value here versus actually waiting for the action selection and then doing it at the next step. Yeah. So any other question about this? Q-learning, how it works? Because then this technique actually can sort of incorporate elements of Q-learning as well. We'll see how, but there is some similarity between this and Q-learning. So expected Sarsa compared to Sarsa is, you can either look at it, it's very similar to both Sarsa and Q-learning. So here, actually, let me go back to the Sarsa update. So this is the Sarsa update. And we can see we have the Q value at the transition state. The difference in expected Sarsa is that we replace this quantity with the expected value under the policy. So in Sarsa, we wait for the policy to make an action selection, and we use the Q value. In expected Sarsa, we look at the current policy that we have, and we try to compute the expected value of the action selection. And here it's written out explicitly where we have a sum over actions of the policy as it is, currently defined. Versus in Sarsa, we actually wait for the action. So these methods, because like the expected value of this is the expected value of this is this expected value. The difference is here we're sampling it, and here we're computing it explicitly. You can see this is also similar to Q-learning because instead of sampling an action, we're doing an explicit computation across actions here. In the case of Q-learning, this is a maximization. In the case of expected Sarsa, this is a sum over the policy. And this is still on policy because, the pi we use here, this is the policy that then gets updated as an epsilon greedy policy. And here, let's see, where's the pseudo? Oh, actually, they don't have pseudocode for expected Sarsa. But yeah, it ends up looking very similar to Q-learning, except here there'd normally be a maximization function, and here it's replaced with a sum over pi. And then the policy is then updated after you update the Q values. But the summary statement is that expected Sarsa does updates in expectation, whereas Sarsa does it with sampling. Actually, wait, do they have a better phrase of that? Sarsa moves in expectation as opposed to moving deterministically. Oh no, sorry. So in Sarsa, it's not deterministic because the value that you use is based on the sampled action from the policy. Whereas expected Sarsa, we're removing the stochastic property from the update, and now it's an explicit calculation using the probabilities of the policy. So the idea is that this should reduce the variance of the updates by doing this calculation, because we actually have access to all the Q values. Now, I did end up running this. So if you run this, like I didn't, this isn't in the book, that they have this plot showing the performance of these algorithms on the cliff world, right? This is for the cliff. Yeah, on the cliff walking task. But we already know that the Q-learning, example, it learns this path that hugs the cliff. Using Sarsa, at least with this learning rate, it ends up using this. Expected Sarsa, apparently, like, what is closer to the optimal path with the epsilon of 0.1 is actually this path, which is actually a little less safe than this path. But because we're removing the variance from the estimate, it's able to learn a slightly more optimal path, right? Because it has a better estimate of the probability of taking a random action because we're computing it explicitly. And you can see that actually under that criteria, expected Sarsa has the best performance on this task. In the, wait, did this thing not load? Wait, to see, where's this figure? Well, this figure in the book is also showing sort of in the long run for this task that expected Sarsa has the best long-term performance under a variety of learning rates. And also, it's also better, I mean, in the short-term performance, it just means you don't have to hyperparameter tune as much for this method to get a good outcome. And that makes sense because we're reducing the variance of the updates by making use of all this. So it's sort of like combining benefits of both methods where we have, you know, like we're still taking into account the epsilon that we get rid of in Q-learning, but then, you know, we have the reduced variance and a better chance of learning the true optimal path that we would get with Q-learning. Yeah, so I don't know. It's just showing like expected Sarsa. This is sort of, again, a backup diagram summarizing how expected Sarsa is different from Q-learning, where instead of taking the max, we're taking the policy. Now, if the policy that you are updating in expected Sarsa, like here, I'm updating the policy in expected Sarsa to be the epsilon greedy policy. And then when we compute the expected value, we're using this. If the policy update was greedy instead of epsilon greedy, then this would actually end up being the same as Q-learning. Or almost, it would be the same as Q-learning in the case of where we didn't follow the epsilon greedy policy in the trajectory, because then when I compute this sum, pi, the policy is only going to be non-zero at the maximizing actions. So this will compute the maximum in this case. And actually, the way Sarsa is set up, you could define both a behavior policy and a target policy. And then what would happen is you would update the behavior policy. You would take the step using the behavior policy. And when you compute the expected value of Q, you would compute that with the target policy. And you could update both of them here. And if your target policy is the greedy policy and the behavior policy is epsilon greedy, that is exactly equivalent to Q-learning. So you could actually implement Q-learning as a variation of expected Sarsa. But it's also more flexible because you could do other things than just that. But I guess the sort of, you know, if you had, and actually the way I've implemented it here, do I have to? I think I might have only done that for a future function. I think it just ends up getting into these other techniques, which I guess we can talk about next time. But for double, yeah. So later on, they introduced this like double Q-learning and double expected Sarsa. So we can get into that next time. But you can always actually do Sarsa where you do have a separate behavior and target policy. Yeah, there's no expected. Whereas with, you know, so Q-learning is just basically a version of expected Sarsa where the target policy is the greedy policy and the behavior policy is the epsilon greedy policy. But yeah, for both Sarsa, for both expected Sarsa and Q-learning, when we do the update, we are explicitly, you know, using the policy to compute it rather than just sampling it from the action space. So I think that sort of concludes all the standard techniques in the chapter. The remainder of the chapter has information on after states and maximization bias, which is, I think it's actually pretty important, but we could cover it next time if people want to stop now. I mean, it's already 8, so I guess it's up to everyone else. I don't know what people think, but yeah, should we move on, or should we just wait until next time to finish chapter 6? It may not
Yeah,
like take the whole next meeting to finish.
Yeah, I'll probably head out.
Mhm.
But thank you very much. This was super cool, especially for my first time. So you've given me a lot to think about, and I'll definitely be reviewing the previous chapters I missed. So thank you.
Yeah, sure. No problem. Yeah. Let me know if you have any issue finding the old notes, but they should all be in that repository.
Yeah, I've been reviewing those kind of throughout the lecture or
Mhm.
the meeting. So yeah, super cool. Thank you.
Okay, great. I'm glad yeah, people learn something. And yeah, if there's any, so we can stop now. If there's any remaining question, you can ask it now. If not, then we can stop and we'll try to finish chapter 6 and maybe start a little bit of chapter 7 for the next meeting.
Thank you so much, Jason.
Okay, great. Thanks. Yeah, we'll see everyone next time.